The purpose of this video is to talk about eigenvalues and eigenvectors for matrix models. When I say matrix models, I mean something along the lines of Leslie matrices or regular Markov chains, although there's a few other matrix models that this would also apply for. Eigenvalues and eigenvectors can seem like these bizarre abstract concepts, but they really are quite powerful for these matrix models. And so what makes eigenstuff so great for matrix models? I'm going to work with a classic model that's kind of like the Leslie matrices, although it's technically not Leslie matrix, as we'll discuss. Suppose we have an insect population that's split up just into juveniles and adults. And then year after year, it's a discrete model. So 1 year into the next and not anything in between. So we'll say now we have a certain number of juveniles, a certain number of adults, and then next year, next season, whatever your timing is, the next tick of the clock, we also have some juveniles and some adults. But the transfers between these depend on the age category. So if you're a juvenile, the average juvenile produces 1/4 of a juvenile for next year. And so say 1/4 of the juveniles produce one juvenile next year. Or maybe the 1/4 are still juveniles next year. The model doesn't distinguish between those. But then of those juveniles, maybe half of them make it to adulthood. The other half are still juveniles or removed from the system, as we could call predation. Adults, say they create, on average, 2 juveniles per adult. And say for next year, maybe 1/4 of them survive from 1 year into the next. A true Leslie matrix, you either have lots of age categories until they hit a no survivors age category, but this will work just as well for us. This gets encoded as a matrix then. If we think about from juveniles, adults, to juveniles, adults, juvenile to juvenile, 1/4, juvenile to adult. Juvenile to adult is 1/2. You have to be careful about this. Adult to juvenile is 2, and then adult to adult is 1/4. And then what we'll do is the way we use this is that say we have in 1 year we have 4 juveniles and 8 adults, which is absurdly small, so maybe it's 4,000 juveniles, 8,000 adults. If we multiply this by 1/4, 2, 1/2, and 1/4, we will get 1/4 times 4 is 1, 2 times 8 is 16, 1/2 times 4 is 2, 1/4 times 8 is 2, so we will have 17 juveniles and 4 adults. Quite a population boom. We'll go from 12 to 21 individuals. So we can do this round by round, year by year, generation by generation to figure out what happens to our population. And so let's take a look at another example, a bit more detailed, maybe perhaps a bit more realistic numbers, although still convenient for this matrix. So our matrix that we're still interested in is 1/2 or 1/4 to 1/2, 1/4. And say we start out with an initial population of 128 juveniles and 512 adults. Well, that means that x1 will be m times x0, which I'm going to skip over the calculations, but that works out to be 1,056 and 192. X2 is that matrix times last year's, the previous year's population figures, but that's also m times x0, if we just replace what x1 came from. So that's really m squared times x0. This all seems like trivialities at the moment, but this will give us some power later on. In any case, regardless of how you get there, it will work out to be 648 and 576. I'm going to stop calculating these just because the numbers get messy. But what you'll see is, as we keep going, x3 is 3 copies of m times x0. I mean, it's also m times x2, but this is what I'm interested in. So it's m to the third in this case times x0, and if I wanted x to the x10, that would be 10 copies of m times x0, and then in general xn, the populations for the nth year, populations for the 10th year, populations for the 3rd year, would be m to the n times x0. And this is what makes Leslie matrices work, and what makes these Markov models work is you can compute whatever power you want, which can be done relatively rapidly to figure out what's going to happen in the future. We can do more than that, though. We can actually use the eigenvalues and eigenvectors of m to tell us something about what happens to xn in the long term. So I'm interested in what happens to x of n as n approaches infinity, as n gets very, very large. That's what eigenvalues and eigenvectors tell us. So I'm going to skip over the calculations for them, but the eigenvalues and eigenvectors, just a quick refresher on how these work of m. These will be, in this case, 5/4 is lambda 1, which has eigenvector 2, 1, and eigenvalue negative 3/4, which is corresponding eigenvector v2, which is negative 2, 1. And what makes these nice is that these are sort of these magic values of the matrix. If we take our matrix M, and I am still using the 1/4 to 1/2, 1/4. If I multiply that by V1, by this matrix, the result that I get is the same as if I had just taken 5/4 times V1. You can grind through the calculations yourself. And in general, if I have any number times V1, this number will show up on both sides, and so it doesn't really matter there. And likewise, if I take m times V2, that'll have the same effect as multiplying by negative 3/4 times V2, only for matrices or only for vectors that look like these, or scalar multiples of them. That's what eigenvalues do. The reason this is nice is that V1 and V2 form, can be called a basis, a different way of looking at population data. And so if we had that, for example, before I get into that, step back, because we're going to be looking at powers. Let's just cover that just to be clear there. If I had a whole string of m's being multiplied together times V1, well, then I would have m minus 1 times m times V1. Those link up to be lambda 1, that's the 5/4, times V1 times all these extra m's, but I could peel off that lambda 1, peel off another one of those m's, m to the n minus 2 times V1, again, pull off another lambda squared, m to the n minus 2 times V1, and so continuing this process, what we'll see is that's the same as multiplying by the eigenvalue n times. Multiplying by the matrix n times is the same as multiplying by the eigenvalue n times. Only if this is an eigenvector, which in this case it is. So that's one thing that's going to be nice. That's going to be a time saver for us, because multiplying by a number to a power is much faster than multiplying by a matrix to a power. Here's the beauty of this, though. Say we had that, again, that x0, which was 512, it was 128 and 512. I can actually rewrite that in terms of some number, we'll call A, times the first eigenvector, plus some number times the other eigenvector. So I'm looking for numbers A and B, A times 2, 1, plus B times negative 2, 1. I'm looking for numbers that do this. You can set up a system of equations if you want to solve it. I've pre-solved it, but this is what it would look like. You set that up, solve that maybe with its own matrix, and you end up with A and B being 288 and 224. And so you can verify this, that 128 and 512 is 288 times 2, 1, plus 224 times negative 2, 1. You can grind through the calculations, adding these and subtracting these, and you'll get these two numbers out there. I'm going to ignore the details of this. I'm going to just, in general, if the eigenvalues are different and a few other conditions there, that x0 is A times that first eigenvector plus some number times that second eigenvector. Well, at this point, we're pretty much on our way. We're off to the races. xn is m to the n times x0, as we discussed. But we can decompose x0 into these two different eigenvectors. So that's m to the n times a times v1, b times v2. Number vector distributive property works for matrix multiplication, and so we're looking at a times m to the n v1 plus, remember a and b are just numbers, and so I can pull them out in front to make things simpler, m to the n times v2. But as we discussed, when you're taking a matrix times an eigenvector for it, that's the same as multiplying by the corresponding eigenvalue, just multiplying by a number raised to that same power. And so what we're seeing here is that the on the nth year, nth generation, whatever, can be written in terms of two arbitrary numbers. I mean, you got to find what they are. They're not anything you want, but numbers based on what the x0 were, times a power of an eigenvalue times an eigenvector, and like a power of an eigenvalue times an eigenvector. This is true regardless of what kind of matrix you're dealing with, so long as you have two different real eigenvalues and a few other conditions. What's nice about this in a lot of cases, in particular the Leslie matrices and the regular Markov chains, is that we are guaranteed by the special Perron-Frobenius theorem that we're going to see the lambda. I'm going to assume lambda 1 is the bigger one of the two. We're guaranteed that it's going to be positive, and that v1 is going to be all positive numbers, which means not only that these other guys are going to be less, or going to be between -1 and 1. That they're going to and what happens to these numbers is they're going to shrink in importance. Let's go back to the original concrete example to really see how this works. And so for the running example that we've been doing here, xn is going to work out to be 288 times that lambda 1, which is 5/4 to the n, times 2, 1. Again, just copying over from this, plus 224 times -3/4 to the n times the vector -2, 1. Well, as n goes to infinity, 5/4 is going to the n is also going to go to infinity. We'll deal with that later. This is going to approach 0, though, because it's between -1 and 1. When you raise it to a huge power, it's going to diminish. You can think of this as diminishing. Regardless of how big the 224 is. So as n approaches infinity, xn is pretty much the same as 288 times 5/4 to the n times 2(1), which, if you're looking at it from a juvenile's adult's perspective, 288 times 2 times 5/4 to the n juveniles, and 288 times 1 times 5/4 to the n adults. Not only that, total, you can add these up, 288 times 3, which I've pre-computed, 864 times 5/4 to the n total. There's a lot going on here, besides just this is the formula. For example, this is exponential growth. Every year that goes by, you are multiplying by the same amount, the factor being 5/4, which in general is going to be your dominant, your largest, your dominant eigenvalue. Notice that there's no guarantee that this dominant eigenvalue is going to be bigger than 1. There is a guarantee by that Frobenius theorem that it's going to be positive, but that it's greater than 1 is not guaranteed. If this had been 3/4 or 1/2, this would be a decaying population. Year after year, it would be multiplying by that number less than 1, by that 3/4 or by that 1/2. It's also possible this magically works out to be a 1, and that happens all the time for absorbing Markov chains. If that's a 1, then we have stability. It's not exponential growth or decay, it's just stable. You're multiplying by 1 to the n year after year. And so there, and that's a stability. So it's not always growth, but it is always multiplying by a number raised to a power. It just depends what that base is, whether it's 1, bigger than 1, or less than 1, that tells you steady growth or decay. So that's the total population is growing exponentially according to the dominant eigenvalue. There's one other thing that we can notice. If we look at juveniles per adult, we got a lot of cancellation happening. You get 2 to 1. That 2-1 was our V1. And that's not a coincidence either. The eigenvector that goes with the eigenvalue tells you long-term distribution of among categories, juveniles to adults. And so we should expect a 2 to 1 ratio of juveniles to adults, roughly, as n gets larger and larger. We should be getting closer and closer to this. The discrepancy from this is based on the second largest eigenvalue. I don't think all the other eigenvalues, but there's only 2 here. And so the dominant eigenvector tells us the long-term age distribution, or whatever the 2 categories are distribution. Now, all of this I've done with a 2x2 matrix with 2 age categories, or 2 states in the Markov chain. It works with more. You can do it with 3, you can do it with 4, but it gets more complicated, and finding them gets more complicated. One last thing I want to mention is there's a whole geometric aspect of this that can easily be overlooked, and that if we had started from, let's say, that initial 128 and 512 population, so this is our juvenile axis, this is our adult axis, and that was our x of 0. We ran that calculation, we end up somewhere around here for our x1. We did that calculation before, what those end up being. You do it again, you end up around here for x2. I'm going to stop writing the x's now. Then 3 ends up here. After 4, you end up around here. 5, you end up around here. 6, you end up around here. So if we connect these dots and watch what happens, what we're seeing, it seems to center around some sort of trend. Now, it should be a straight line, but I've been too sloppy with drawing those points. That line has slope 1/2 which is not unlike our 2-to-1 ratio of juveniles to adults. It's backwards because of the way that how the axes are arranged. But these will, as time goes on, bounce around this center tendency here, this 1/2, this eigenvector. Also, how far these are from the origin is related to the total population, and that is also growing exponentially as time goes on. So there really is a center here. For a 3x3 case, we'd be drawing this in 3 dimensions, and they'd be centering around some sort of central tendency. 4th dimensional, it gets a bit harder to draw. Thank you very much. I hope this helped clear up some of the confusion about how do eigenvectors and eigenvalues have anything to do with matrix models. Thank you.